So, dear ladies and gentlemen, we are now coming back to our studio. So I hope that you already take 1 or 2 breaths, because this break was, well, too small, because, well, our last presenter was a little bit out of schedule, but I hope that you enjoyed with the speech. Now we will start our session, and the session chairman should be Professor Viktor Krasnoproshin. So unfortunately, I will be a chairman, not him. But anyway, I hope all of our presentations and all of our presenters are here. Now I would like to give a floor to the first presenter. So the presenter, who will let's say present the paper report called Parallelizing by Smart Tiling by Sergey, Sushko, Alexander Chemeris, and Svetlana Reznikova. So please, colleagues, you have a floor now. You may start your screen, share the screen, and go with your presentation. Thank you.
Thank you very much. Can you see my
Yes, exactly. You may proceed.
Okay, thank you very much. My name is Sergei Sushko. Me and Dr. Alexander Chemeris and Svetlana Reznikova prepared a presentation for you. And all of us, we are representing of National Academy of Science of Ukraine. So I'm very happy to be for the first time in this conference and share with you my investigations. My report will be dedicated to the software optimization topic. It's quite a big task. And as you can see on my title, it's Parallelizing but Smart Tiling. So smart tiling is a new method proposed by our team. And I'll describe it with you during this presentation. So let's make short focus on optimization issues. So first of all, where it can be applied. Actually, it can be applied everywhere for some mobile application, for some embedded servers, grid, and so on. So in any case, optimization gives us some new opportunity, like more functionality, more features, or some less power consumption and less cost of holding of the servers. So it's every time it makes some benefits. From the other side, it's manual optimization. It's a long and quite tedious way, and it requires a lot of skills from software engineers to do it. And actually, it's not is done in best way. So in common, several stages of optimization can be highlighted. Top one is algorithm optimization. It's usually what mathematicians and sometimes a software engineer do. And it's the highest level. So it's a global approach, global algorithm, which should be realized in software source code. So second one is like microcode optimization. It's regarding the some usage of commands, sequence of it, and like a better representation for the compiler. And the last one, it's microcode optimization. It's actually what CPU will have after compilation. So, my scope is about second stage. It's optimization of command sequence. Actually, it's quite optimistic because we can change the code in different ways and optimize it somehow, and again use it with existing compilers. So this way allows us not only to use some specific feature, but it allows to be hardware and compiler independent. So we can change something and don't care about where it will be applied. So in common, we have let's say, a big problem of proper selection of optimization methods. So we can have a lot of methods which pointed with letter M, and some parameters of these methods is letter P. So, and for every part of code with index I, it can be some specific set of these methods and its parameters to obtain the best parameter which have to be optimized. For example, and usually it's computational time, but sometimes it's data memory size, program memory, energy consumption, and so on. So the big deal is to find these parameters in every specific algorithm, and not algorithm, even for program, for particular hardware. So if we are looking in the big list of existing some optimization methods, actually it's for speed up, it's usually optimization of computational loops, because it's quite small part of the program, but it's quite big impact on the total time execution. So as you can see, there are a lot of methods, and it's not the full list of it. And in some cases, it's one of them are better, another worse, and also some of the methods can be combined together. So as you understand, it's quite a big bunch of possible combinations and its parameters. So in my work, I was focused on parallelization. It's quite obvious that we have a lot of hardware units, computational, and CPU, and so on. So if we can divide some tasks onto smaller tasks, it's better to do it. It's obvious. And another quite promising method, named tiling. It's quite different way. It's not related to the cores, but it's divides iterative space of processing onto smaller blocks, which can be which reduce memory continuity, and also these tiles can be divided also in parallelization by several cores. For example, let's have a look on small example. It reproduces two-dimensional loops with I and J indexes from some restriction from 2 to 9 and from 1 till 9 also. And as you can see, it's blue rounds. It's actually some iterative points when something should be computed. It doesn't matter what exactly. And gray rectangular, it's actually tiles. So for the first case, we divided 4 by 3. And for second one, we divided 3 by 3.
Excuse me. Pardon. So we can't see currently your screen. Could you share that again?
Sorry?
Yes. Your presentation. Or
no.
Not. Okay. Well, so just camera. Yes.
Oh, I show you my screen. Can you see it?
No, yet. Not yet.
Oh, so it's slide number 7.
that's okay actually. So because the oral presentation is also okay, but when you show in the formula, so of course it's better to see your screen. And our participants just claiming that they didn't see your screen. Yes, it was at the beginning, but now not.
Just a second. Okay, share screen. Screen number 2. And okay, can you see it now?
No, unfortunately.
Let me check again. Share screen.
Yes, now it's coming. It's loading. Yes, let's proceed with the slide number 7. Let's say, yeah.
Okay. some preliminary information. And let's continue.
That's okay.
Slide number 7.
Thank you.
Thank you for the information. So we have different talent division for 2 cases. And in common, it could be different because 4x3 and 3x3, as I understand, it could be thousands and even millions of iterations per loop. So it can be tens, thousands, or different particular values. And it's not clear which one we need to choose for better performance. But further, I will show you how to find out it properly. What's the main approach? The main approach is that we can use tiling methods, which is a source-to-source transformation. It means that line of this method doesn't produce any binary code. It produces some another source code. So in the first case, usually we do it this way. Like we have some source code, we compile it and execute the program. In this case, we inject some source code transformation before compilation, and then do our execution as always. So now several frameworks are available to do it. I use it Pluto, which has a lot of some blocks. Actually, source code transformation is only one of it, and another one is some additional stuff which allows to transform of the original source code to the polyhedral model, which Pluto works, and then after all the stuff, it produces another source code. So it looks quite ugly if you compare it with the previous one, but it does the work. So when we back to the previous slide about this tiling, what I made, I use it a lot of tiling blocks to the several, quite a lot of test programs, and just verify, does it make sense to change these tile sizes or it doesn't matter? So on these slides, you can see four pictures which represent of different types of time execution. For the horizontal lines in the every slide, it's two tile sizes. And vertical axis is execution time. So as you can see, for every test, when we change in some range our tile sizes, we can obtain a completely different execution time. Which means that if we want to use the maximum of speed up of the tiling method, we need to choose these tile sizes exactly very, very carefully, very particular for every test. For example, in the bad case, if we will be here, it means that we can speed up the program in tens of percents if we will change it slightly. And for different pictures also. And also what I would like to highlight, it's about the pattern of the every picture. So also, as you can see, it's completely different. You know, some plateau like here, and can be some waves, some waterfalls, some hills. It depends on the particular test, and there are no some pattern of it. So the big deal is to find some local minimum in every test, but we don't do it very simple because it's because of the picture, because of the pattern. So we need to choose such methods of the sorting of the better set of tiles, which allows us to find it over very different patterns. Also, I made some new metrics, which actually they show us how bad we can be in when we choose the bad style sizes in mean and in worst cases. So it means that for some tested, if it's in worst case, we can several times less actually more in time execution. And for some parallelizing, it's even be some huge values. So it's really the case when we need to choose these time sizes properly. And what I use it to do it, it's a particle swarm optimization method. It's quite known method of optimization. It has some iteration formula with for every particle, which is multi-agent of method, which can find the local minimum or maximum in the every possible field of search. So every particle has its own coordinates, which moves around some points and trying to find the local and global minimum. Why also this method is good for our case? It's because it has actually some coefficients of social behavior. It means that every point knows about another point local minimum. And to show you how it works, I found some example of it, and you can see that some crosses trying to find some minimum which and tend to stick together. But for my case, it should be discrete particle optimization method because number of iteration of computational loops is obviously integer, and we have some integer grid which are for our case. So what we are proposed, it's actually smart tiling method. What does it have inside it? We have some initialization part, which starts before the every run, and two main blocks of it. It's actually discrete particle swap optimization method, which trying to choose the proper size tiles, which determined by the formula on the slides. And also it uses existing tiling methods and parallelization together. Actually, parallelization can be omitted and it will still works. And how does it work? It proposes some initial points of particles in the proposed range and check and uses tiling methods, which does the code, the compilation of the code and measurement of the existing time, because we don't have any information till we actually measure the actual time. And if we meet some goals or reach the maximum iteration, we stop the algorithm, but in otherwise, we can to change the particle speed and actually again coordinates, and coordinates means that it's values of style sizes. And again, tiling methods will be applied with the different style sizes and measure time and so on, so on, so on, and until we will have some required values or just some better values. So this is, as you can see, an iterative method. So it takes some time to reproduce and to measure all this stuff, but it's quite better because it's try to find some better values, not just one like default or some predefined. So to verify it, I made some measures of the source of the time and minimum values, and it usually requires less time after that, but it requires some time to obtain these values. And also I compared the original execution time aligned to 100%. It's white columns, and gray columns is applying an of tiling methods. And from the left side, it's like only single tile. From the right side, it's tile with parallelization. The darkest one is using of smart tiling method. And as you can see, if we had some 100% tiling, sometimes very significantly speed it up, sometimes not, and sometimes makes even worse. But when we are using smart tiling, it gives us a little bit more speed up against the original tiling method. So in this case, it's okay to use it, and just to remind that it requires some time to obtain this optimal values. And the same feature for the parallelization, even more, because it utilizes all the cores of the processors. So if algorithm is quite good on parallelization, it will be even better with smart tiling. So small conclusion. We have new methods which based on existing tiling method and discrete particle optimization method, which allows to optimize software more and produces better results than original tiling method. Okay, thank you, and I'm ready to answer all the questions.
Thank you for your presentation. So, although we are out of schedule, I think it's good to ask some questions to you. So please, participants, do not be shy. So you can ask questions anyway. Okay, we have no questions now in Zoom or in Telegram chat, and in YouTube chat also we have no questions. I think we need to proceed. Well, anyway, so because we are now online, we are able to make shorter the big break. So it means be in frame of times, but feel free to present the full presentation of yours. I will not interrupt you, but still, so try to be in time. Well, our next presenter will give a report about graph-based recognition of high-level structures in transistor circuits. So please, you have a floor, Liudmila. Yeah, we see your camera, so now it's good to have a screen sharing also. Unfortunately, we can't hear you. Probably it's good to open the mic. So we're still in silence. Are you hearing us? Because we can't hear you. I think something with the mic. Yeah, you should unmute you. Now again, you mute. Please unmute yourself. So our colleagues will try to help you remotely. If not, probably please try to fix yourself. No, we can't hear you. This is because of your mic, probably. Well, I'm just want to probably Liudmila will try to solve it. I would like to announce that all papers which were submitted, which were reviewed, and which will be presented here in these 4 days will be published in proceedings and open license on the website, and it can be downloaded on the website. After the second revision, we will select and the selected papers also will be published in Springer's proceedings. So according to that rule, which were on our website also. So unfortunately, we can't hear you now. Let's go to the next presentation. Sergey Dvoenko and Denis Pshenichny, A1.3 metric corrections of similarities based on orthogonal decomposition. So if you're ready, some of you, so any of you.
Yes, I'm ready. Can you hear me?
Yes.
I asked to give me the screen from the previous report.
Okay. So?
Previous reporter need to close his demonstration.
Yes, but she's, well, yes, we have some.
Do you hear me?
Now, yes. Yes, now. So, yes.
Yes.
Sergey,
so,
please.
I would like to
hold on.
Your topic, graph-based methods of recognition of high-level structures in transistor circuit. I am Liudmila Cheremisinova from United Institute of Information Problems. Так. Отлично. The considered problem is to decompile a flat transistor circuit. That is to convert it into a network of logical networks, of logical gates. First, the decompilation problem was used to accelerating simulation and verification of large VLCE system with many millions of transistors. Then it was used for re-engineering to change it with new basis technological and to detect trials and design changes. What is a GÉANT? We suggested the program of decompilation and graph-based methods for solving some key tasks of decompilation program. Wherein we used the well-known tasks and graph methods, integrating and modifying them to process special types of large data in a short time. The proposed methods are implemented in C++ and some experiment on practical transistors systems show that it can treat it with large circuits in polynomial time in the number of transistors.
Unfortunately, we can't see your screen currently. So probably you stopped sharing it.
Static MOS circuits. Отключилась демонстрация экрана? Да. Так. И что? Data representation. The source and resulting circuit netlists are presented in SPICE format. Each transistor in this format is specified by 4 labels. Correspond to drain, gate, source, and substrate of each transistor. The convenient and natural way to present such a transistor circuit is to use bipartite undirected graph as such graph. And in software presentation, such a graph is the array of nets.
Could you try to show your presentation?
Presentation.
Could you try to show your presentation?
Да что? Иди помоги. Ну что ты? Где?
Демонстрация экрана. Выбрать ее. Где там? Да.
Okay, now we can see.
We suggest graph-based methods for solving some key tasks of the decompilation program. Wherein we use well-known tasks for graph methods and solve it. Well-defined static MOS circuit allows to split it into smaller sub-circuits, each of which is a group of channel-connected transistors. Such a circuit component consists of transistors connected with their drain and source terminals, and it provides signal to pass through power and input terminals. Here, an example of grouping transistor circuit into two channel-connected sequences is shown. In graph interpretation, splitting a transistor circuit in sequences transistors is reduced to search of connectivity components in the graph that represents the circuit. The graph for these purposes is transformed by connecting their drain and source terminals and deleting gate terminals. So we have such a graph, and the task of searching for groups of channel-connected transistors is reduced to the search for connectivity components of the graph. There are two such components. Well-defined transistor circuit is a group of two blocks. Pull-down block consisting of NMOS transistors and pull-up block consisting of PMOS transistors. The blocks are dual, represent dual structures, have the same number of transistors in them, and realize mutually inverse functions. Here a group of two channel-connected transistors is shown, and the group of channel-connected transistors on the right is NAND transistors, and on the left is not CMOS transistors, because it has its blocks have different numbers of transistors. Logic function expression that is implemented by pull-down or pull-up networks is formed by tracing passes between power terminals and connection point. Each pass gives a conjunction of the connectivity variables fed to gate terminals. The OR of all conjunctions yields conductivity function in disjunctive normal form. For CMOS gate, the functions implemented by these blocks must be complementary. Otherwise, the structure is not a CMOS gate. To classify CMOS gates, the conductivity functions are represented in a canonical form that is obtained by factoring, algebraic factoring the expressions. However, not all functionally equivalent CMOS gates are topologically identical. That is because of specifics of topological implementation of CMOS gates. For example, the drain and source terminal can be interchanged. Here is an example of such exchanging drain and source terminals, and so the structures are not isomorphic. The topological equivalence of CMOS gate implementations is established by checking whether the corresponding graphs are isomorphic. Here in the table, some experimental results with decompilation problem are shown. Here for each circuit, we can see numbers of N and PMOS transistors, number of found pass gates, and found channel connected components, and then the number of CMOS gates found among channel connected components. Two last columns show the number of classes of functionally equivalent CMOS gates and the number of CMOS gates that are topologically identical. We can see that among functionally identical CMOS gates, practically always there are topologically non-identical. To check isomorphism between graphs presenting transistor subcircuits, they are complemented with edges connected their 4 terminals for each transistor. Then analyzed subcircuit is represented by undirected vertex-colored graph, and that graph is sparse. So we can see transistor circuits, their graph, and the graph that is transformed by connecting their terminals. In graph interpretation, the isomorphism testing between graphs consists in comparing their canonical forms, isomorphs. The analyzed graphs are constructed by one by, and each of them, its vertical canonical labeling is generated and hash computed. Canonical labeling is done by the process of building the sequence of partitions for the set of graph vertices. They define an ordering of graph vertices. Graphs with equal hashes are isomorphic, and they are changed in hierarchical space with description of their canonical isomorphs. The proposed methods of computing canonical isomorphs provides fast processing of large and sparse graph. Our graphs are exactly the same, sparse and large. Here is an example where we see the initial partition, vertex partition. It is obtained according to vertex types and degrees. So in the same class, the vertices with the same type and the same degree are included. Here we can see different canonization results for two transistor circuits that they are slightly different. And the difference is the interchanging of their drain and source terminals. Here is the different order. Two kinds of experiments with the developed program were performed. With circuits obtained by CAD systems. In this case, full coverage with logic gates was obtained, and with transistor circuits extracted from layout. Here, the coverage is about 60–70%. In all cases, extracted circuits successfully passed through the verification check. Some experience results are shown in the table. Here we see the complexity of the circuit, then the velocity of the methods. It is estimated in seconds and estimated by the number of transistors processed per second, and the number of logic gates that are recognized in the process of decompilation program. And so the conclusion. We propose graph-based methods for solving the task of decompilation flat transistor circuits in the case when cell library is unknown. And the proposed methods are implemented in C++ as a part of decompilation program. Our future work is to extend the decompilation program with means of recognizing memory and more complex elements. Thank you very much for your attention.
Thank you very much. So while I'm asking for questions of our participants, the next speaker, please try to check the connection and try to yes, please close your screen now. Close the session. Stop sharing the screen.
Так.
You need to stop sharing. Вы должны выключить
I
экран.
don't see the no.
It should be a green button which displays that you launching your screen. Please stop this.
Ага, вот. Так, в чем дело? А?
Okay, thank you. So the next speaker, please try to speed up your connection. I'm sure you will be succeed with this. So Sergey Dvoenko and Denis Pshenichny, metric corrections of similarities based on orthogonal decomposition. Please, the floor is yours.
Okay, dear colleagues, can you hear me?
We see your screen, thank you.
Yes. My screen is here. So, metric correction of similarities based on orthogonal decomposition from Tula, Russia. Table contents. The idea of decomposition, correction, using proposed to some small real data. So, raw data is a model machine learning. In model machine learning, usually appear as similarities or similarities. And the positive definite similarity matrix represents a limited set of elements immersed in some metric space, usually like Euclidean space. And you usually use the matrix with similarities considered as a scalar products. In the case of a non-positive definite similarity matrix, it needs metric correction to be considered as scalar products. Previous achievements. We have developed novel end-to-end correction technology for optimal recovery of a violated matrix. This approach differs from the well-known multidimensional scaling problem since it doesn't need to recover explicitly the feature space. The technology novelty consists in each metric violation is connected with some member of the set which is supposed to be responsible for the violation in the usual traditional approach, which does not supposed. So, what traditional approach? The non-discrete Karkanin law of expansion usually used to reduce the dimensionality of the similarity matrix by removing eigenvectors corresponding to negative eigenvalues. As a result, we can calculate a new similarity matrix of the reduced sides to correctly immersed members of the limited set in a reduced space of eigenvectors corresponding only to positive eigenvalues. So the data dispersion is reduced. The novelty of our approach. Empirical functions for paired comparisons are not usually correct mathematical functions of distances or similarities as a scalar products. So according to our novel metric correction here, based on the well-known orthogonal decomposition of a similarity matrix, we propose not to remove but to change negative eigenvalues to become positive ones. As a result, such an optimal correction preserves the dimensionality and of dispersion of raw data. So what does it mean, decomposition? We have a set of n objects represented by normalized matrix S of paired comparisons with normalized elements as units on the main diagonal and other non-diagonal methods between the unit by module. So the spectral decomposition of this non-degenerated matrix has the form: the A is the matrix of the eigenvector columns. This is an orthogonal matrix. And this is a normalized eigenvectors. So E is a unit matrix, lambda is a diagonal matrix of the eigenvalues. And these eigenvalues are positive and ordered in the descending order. This set of an object is correctly immersed in some metric, usually Euclidean space, of the dimensionality not more than n. This matrix S consists of normalized scalar products of objects. The raw data matrix X and the feature space with dimensionality M with dimensionality not more than M are not presented here. We suppose this space has been lost. Otherwise, we can directly calculate scalar products of objects. Based on the decomposition of S, of the non-degenerated, this matrix is not degenerated, the diagonal matrix lambda is decomposed as shown. So you can see trace of this lambda matrix is a trace of matrix S and is a dimensionality of the space. What does it mean, correction of metric violation? In data analysis, the decomposition in terms of orthogonal vectors usually used for the correlation matrix of features, targeted to reduce the dimensionality of the space of eigenvectors of the correlation matrix R to the new value less than initial in different tasks. In particular, the non-correct matrix R has negative eigenvalues, hence the projection of raw data matrix X in the new orthogonal subspace is usually used. It is important to note such the projection requires the raw data matrix X itself to get new one, X prime. In this case, the dispersion for raw data, the total dispersion, is reduced to the new size M prime. Unlike the classical approach, the spectral decomposition in our investigation induced to the set members represented only by scalar products. Scalar products in the non-positive quadrant of the metric space used as the similarities. It doesn't not matter for us what they are, features or objects themselves. In the case of metric violations, in the set configuration, in a hypothetical space, we have noted the spectral decomposition of the matrix S has negative eigenvalues. So we propose here not to reduce raw data, but replace negative eigenvalues in the decomposition by the appropriate positive values to get as a result new matrix lambda under the cap of the same dimensionality. Finally, the matrix S under the wave is recovered in the form of such decomposition. Nevertheless, the new matrix S under the wave appears to be non-normalized, so we need to normalize it to get the diagonal elements as units. After that, the trace of this matrix will be not more than n. So normalization is represented here. So after that, we can decompose the S under the hat again. And after this, we can see that the trace of the new matrix S under hat is n. Consequences and opportunities of this new problem. The raw similarity matrix can have other type of violations. For example, with non-diagonal elements exceed diagonals 1 by the model. It is possible in general to formulate any suitable problems to find the corresponding set of eigenvalues for similarity matrices. For example, to provide a suitable conditionality. What does it mean using the proposed approach for real data? Example, the psychologist Nibelitsyn obtained data during his investigation of light sound sensations imposed by rhythms in the form of correlation matrix. It represents statistical interconnections between power biorhythms of 11 frequencies of brain, like alpha, beta, and theta rhythms in electroencephalograms. So this is the example of this correlation matrix. This matrix contains 10 positive and 1 negative eigenvalue, so it has metric violations. You have already studied this matrix in order to correct it and determine the optimal conditionality based on the end-to-end metric correction technology from the previous investigation, as a result of the previous investigations. So here is the example of the corrected matrix. We try to replace the negative eigenvalues from the negative to some small positive to get minimal corrections of the initial matrix. So the conditionality of the matrix is too bad. you can see is 122,000. So, early, a statistically inspired condition of this matrix give us the conditionality is about 60. And now we replace a negative eigenvalue with a positive value. 0.612. And after the normalization, we can get the correct matrix with positive eigenvalues, and with the last eigenvalue is 0.06. So the final conditionality is practically optimal. As you can see, these matrices are practically the same. Initial, recovered, and recovered optimally. So the optimality of all corrections are based on the cardinal law properties of the orthogonal decomposition. So what does it mean as conclusion? Optimality of the correction is supported by the properties of the cardinal law of expansion and the correct selecting of the new value of the corresponding eigenvalue. Here we face the well-known perturbation theory of eigenvalue problems. This is the one of the first publications of Relish. In the framework of this general theory, the node of our approach consists in the attempt to make a perturbation in eigenvalues first, to recover then the similarity matrices second used in machine learning. That's all. Thank you for attention.
Thank you, Sergey. Thank you for your very intensive presentation, and I hope you will start chatting with those who will ask you questions using our chat in Zoom. So now I need to proceed with the fourth presentation, which will be made by one of the co-authors, Viktor Krasnoproshin, Vadim Rodchenko, and Anna Karkanitsa. Pattern recognition based on class distinctive features. Please, you have a floor. Please share the screen and start the presentation. Thank you. Now we see your screen. Thank you.
Okay. Good afternoon, dear colleagues. It is my pleasure to participate in the conference. And let me present the research that was done together with my colleagues, Viktor Krasnoproshin and Vadim Rodchenko. So, pattern recognition based on classes' distinctive features. So if we return to primary sources and recall the definition of data mining coined by Gregory Petetsky-Shapiro, it says that the main goal of data mining is to identify in data a previously unknown, non-trivial, and potentially useful and interpretable knowledge. And this knowledge can be used for decision making. So now let's have a look at the simplified scheme of machine learning process and data mining process. So in machine learning, we take as an input the training set and the testing set. And the learning process is focused on building an algorithm on the base of the training set. And this algorithm is usually the classification algorithm that can be used to classify the testing sample. So the main output of the learning process here is algorithm. In data mining, we have a bit different approach, how the learning process is implemented. So we take a training set as an input, and we are expecting to get a knowledge. And this knowledge will be used to construct the classifying algorithm that allows us to classify objects. So the practical usage of the explained scenario revealed to a number of shortcomings, or let's say disadvantages. Firstly, with machine learning, when we are preparing the training set, it is actually time-consuming process. In some cases, it takes 80% of overall effort and usually involves experts. Secondly, selecting a family, or let's say the model of algorithms, it is a non-trivial task. Usually data scientists do it. So again, the process involves some experts. And that's why we can conclude that learning can be implemented only in automated mode, not automatic mode. The resulting algorithm that we will get looks like a black box. So the algorithm that can be hardly interpreted. And even if these algorithms approximate the unknown dependency, we don't have too much knowledge about this algorithm. That's why we call it black box. And finally, even if an algorithm is found, it is based on the training set. So it means we still don't have information. Are there any other feature subspaces where the problem is solved more efficiently? So the main output of this explanation is to explain that our algorithm that we get as a result of the learning process, actually algorithm that we can trust, but that can be hardly interpreted. So to overcome the mentioned disadvantages, we propose the alternative approach. And this approach is based on the hypothesis of compactness. So in the object space, classes form compactly localized subsets. So again, if we go back to traditional approach in the learning process, it is reduced to the construction of decision rules. The decision rules are based on a priori specified, or they are priori specified, even up to parameters. So the learning process involves searching of these parameter values. The alternative approach is based on the idea that we are searching such combinations of features that are most informative to distinguish classes. And this combination of features will be taken also from the priori dictionary of features. Identification of the features occurs as a result of constructing a feature spaces where class patterns do not intersect. So to show the alternative approach, we can have a look at this geometrical representation. In the traditional approach, we are building a function, let's say function that is shown here as a line, and it depends on some number of parameters, and it looks like it splits the overall set into regions. In the alternative approach, we are trying to build feature subspaces that allows us to classify objects. So if, for example, there are two features, X and Y, we are expecting that these features will uniquely identify objects from the training set. And now a few words about the statement of the recognition problem. Based on the proposed idea, we would like to present another problem statement of the recognition problem. So in contrast with the traditional approach, it is required to construct an algorithm that would approximate the target dependency on the entire set of object X. In the alternative approach, it is required to find a feature subspaces where class patterns do not intersect. And based on these patterns, the next step is to construct an algorithm that would approximate the target dependency on the entire set. And this second step will be very simplified, because if the feature subspaces is known, so the process of constructing the algorithm becomes trivial. So to implement this idea, the supervised learning algorithm was designed. So let's say that we have a training set, and this set is formed on the basis of so-called a priori dictionary of features F. Let's also V be a set of all possible combinations of features from F. So we are going to build class patterns in the form of cluster structures based on the training set. And the priori dictionary of features will be used. So in this slide, there are steps of the design algorithm, and the algorithm is aimed to construct a set of features where class patterns do not intersect. So let me skip these steps, because the general idea of the algorithm is explained, and in details algorithm is described in the published paper. Okay, so now it is important to analyze what is the outputs of the algorithm. So after the algorithm execution, the set of feature subspaces will be constructed. Each combination of features from the set defines a decision space in which class patterns do not intersect. So based on this combination, we formulate the previously hidden and empirically revealed pattern. In the feature space of subset Vi, class patterns do not intersect. So we are getting a knowledge about feature subspaces that allows us to classify objects. Within a specific applied problem, the revealed combination of features can be interpreted by the domain expert. And this is the important issue, because in contrast with the black box that we have in the machine learning process, this approach allows us to have knowledge, so kind of white box that can be interpreted by the expert. To show and prove the efficiency of the approach, let's have a look at the results of the numerical experiment. To explain it in simple way, we are taking a simple data set where we have 20,000 7-bit integers, including 10,000 multiplies and 10,000 not multiplies by 5. So from mathematics, we all know that number multiplies by 5 if it ends with 0 digit or digit 5. So applying the design algorithm for the given data set, we will analyze possible combinations of features from the set V. So like units, tens, hundreds, thousands, tens of thousands, and so on. So the table that is shown on the slide demonstrates that we got the M5 set and an M5 set. So numbers multiplies of 5 and numbers not multiplies by 5. And the conclusion from these results is that M5 have no digits 1, 2, 3, and so on 9 at the unit place. And the set M5 have no digits 0, 5 at the units place. So it is also clear that 0 here and 0 here says that our class patterns do not intersect. If the same experiment will be done for feature hundreds and thousands, or tens of hundreds and hundreds of thousands, and even millions, we see the intersection of classes. So, and it simply proves that we have actually only one feature unit that allows us to classify objects. So analyzing all of the features and possible combinations of features, we got intersection equals to 0 only for the feature units. So the feature units provides an absolute separation of classes of numbers that multiplies of 5 and not multiplies of 5, since we got interaction that is 0. And it is also important to note that the algorithm running time is 0.35 seconds. That is faster than comparing with the same approach that was described for the learning process in machine learning. So these experiments allows us to conclude that alternative approach based on searching the feature subspaces can be efficiently used to pattern recognition and object classification. So as a conclusion of our research, we can say that as a result of the research, an alternative statement of recognition problem is proposed. An alternative approach to learning process is also proposed, and this approach ensures class separation. For that approach, the supervised learning algorithm is designed, and it is aiming to find informative combinations of features that helps us to classify objects. And this algorithm allows also to detect previously unknown dependency, and this dependency can be interpreted in terms of the subject domain. The effectiveness of the approach is confirmed by the results of the numerical experimental model data. That's all. Thank you for your attention.
Thank you very much for your approach to the pattern recognition problems. So if we have no questions, so I'm just asking to those who are in our Zoom session. So now I'm passing the focus to the next presentation, new algorithm for building effective model from prediction models and using parallel data, which will be presented one of the co-authors, Zurab Gasitashvili, Merab, Phkhovelishvili, I'm sorry for my pronunciation, and Natela Archvadze. Please, you have a floor now. So you muted, yeah, now we have a focus on you, but please unmute your microphone. Yes, now we see you.
Sorry, do you hear me?
Yeah, we hear you, but quite a big echo.
Hello?
Hello.
Yes, okay. I would like to share the screen.
You need to turn off your sound from the second computer.
Yes,
yeah,
exactly.
I turned it off. I turned it off.
Yeah, that's nice.
Okay,
perfect.
Is okay.
Now please
so now,
show us your screen.
Yes? Just a moment. One second, sorry.
That's okay, yes.
We are trying to share presentation on the screen. But I will start anyway, and okay. Building much more effective new hybrid model for prediction models using parallel data is discussed. The algorithm for selection of model pairs and its advantage over any best prediction model is provided. Some prediction models are based on using of parallel data, although it must be noted that the term parallel data is definitely explained in each of them. In practice, parallel data is used during prediction of various... do you see the presentation, sorry? Hello?
No, we do not see your presentation. We just see your camera.
Okay.
We see you, but we do not see your presentation.
Okay, I continue. Sorry. We are trying to share it, but cannot share.
Sorry to show your screen.
If I go out and turn again, maybe it will help.
Okay, please try.
Okay, one second, sorry.
Yeah, while our colleagues is trying to connect to share the screen, I would like to say that we divided our conference into two sessions. The first session, A, means the problems about pattern recognition. So these theoretical problems according to the papers you presented to us. The second session is about more applied things, image analysis and so on. So it's also pattern recognition, but more practical one. So each day we will have 2 or 3 sessions which devoted to pattern recognition and image processing, applied problems, or vice versa. So this how our conference is divided into two. After the lunch break, we call it big break, we will have a session about the practical problems. So I think I will also be a chairman of this conference. So now finally we see your screen. Please proceed with the presentation. Thank you.
Sorry for the delay. Yes, sorry for the delay. We start. New algorithm for building effective model for prediction model using parallel data. So, building much more effective new hybrid models from prediction models using parallel data is discussed. The algorithm for selection of model pairs is advantage over any best prediction model is provided. Some prediction models are based on using of parallel data, although it must be noted that the term parallel data is definitely explained in each of them. In practice, parallel data is used during prediction of various events, including natural disasters, earthquake, landslide, tsunami, mud flow, and etc. For prediction economical, political events, for effective solving of prediction tasks in the sphere of medicine and other fields. The definition of parallel data is based on introduction of new type of dependence between the data, which is called parallelism between the data. The definition of parallel data is based on introduction of new type of dependence between the data, which is called parallelism between the data. Parallelism between the data is mutual dependence between those data which are used for prediction of the same event. Various data may exist in different periods, parallel by time or location, parallel by location. Now, success probability of this prediction. On this slide, we describe the main idea of algorithms for building of prediction models is reviewed by us through parallel data. Let us assume that there are several models of prediction. From them, it is necessary to select such pairs, triples, for several models, which give much better results than a single best model from them or two models separately. This algorithm was the following. Such models were found for which the number of coincidences of unsuccessful predictions for some given event was as low as possible, but successful predictions were necessary for them. In this article, we will establish 5 lemmas for the task of static prediction and show how the accuracy of such models is increased through our algorithm. Specific data are taken from earthquake prediction task. Each prediction model is built based on certain predecessors. For earthquake, the predecessor is geophysical phenomena, mainly, which precedes the actual earthquake. Assume that we have several prediction models, which provide some predictions through their predecessors. For example, for earthquakes, when it would occur, and which location and with which magnitude. We study history. Let's assume that there is plenty of data and it is necessary to calculate, based on predecessors, how many times the prediction of earthquake occurrence was given and how many times actual earthquake occurred. Assume that we consider the necessary predecessors and the models created for them, A1, A2, and AN, okay? We calculated the number of earthquakes predicted by each predecessor, P1, P2, Pn. For each Pi, let's calculate quotient of M, the number of actually occurred earthquakes, write it in percentage and designate with Ki equals M/Pi 100%. Put the sequence of model success in descending order, and this sequence denotes as K1, K2, Kn. Lemma 1, if such pairs of models are selected for which the number of coincidences of unsuccessful predictions for some given event was as low as possible, but successful predictions were necessary for them, then the success probability calculated for combination of any pair so selected is always higher than or equal to the success probability of best from them. If we take best Ki and pair it with any, even the worst value Kg, then their combined result is not worse than Ki. If we take the best Ki and pair it with any, even the worst value Kg, then their combined result, as I already mentioned, is not worse than Ki. Proof is based on the fact that for the pair Ki and Kg, where Ki is less than Kg, then the intersection of their successes, of course, is less than or equal to Ki. Lemma 2. The higher number of intersections of prediction models, the better prediction we would get. For example, the best triplet combination of 3 predictions would give better results than the best pair of prediction. The best quad gives better results than the best triplet, and so on. Now, if we talk about lemma 4, modification of prediction model, it means recalculation should be done from the day of the last earthquake occurrence. In accordance with lemma 2, the prediction pairs are selected. When selecting them, we determine the number of accurate coincidences of predictions. Lemma 5, when selecting the pairs of prediction models, an approximate coincidence should be taken into account. And now, the conclusion. We considered the possibility to build much more effective new hybrid models from prediction models using parallel data, and by means of lemmas, we state that the advantage of selection of model pairs over any best model of prediction, it was shown that the more is the number of model pairs, the more is advantage of the lesser number of pairs. The best pair is the one that does not have intersection between each except actual occurred prediction. When to reselect the pairs of prediction models, and that is necessary to consider approximate coincidences of predictions in this case. This is the literature which lists articles by authors on the topic, and finally, sorry for technical problems, and thank you for your attention.
Many thanks. I should say that finally it was okay, so your presentation was good. And I hope that all of us will have a chance, actually we'll have a chance to chat. I remind you that there is a worldwide YouTube stream now. So we have an audience on YouTube. We have participants on Zoom. So please start chatting, ask questions.
Alexei, I would
yes,
like
exactly.
to ask a question.
Yes, of course. Yes.
Alexei, I would like to ask a question.
Yes, of course. You have a floor now. Please ask the question.
Yeah. Okay. Thank you very much for your presentation. I would like to ask you whether you have any examples where you applied your predictive model for solving some application problems, or just a theoretical one.
For application of this model, a lot of data are required. Big volume of data. While earthquake, this data which we possess are few. We don't have a big range of data. We were able to do it for the prognosis of valued course. And we did it. And we saw that our model identified the pairs which gave us an advanced better results. If we will have more, possibility, more data for application of this model in different other directions, we will be able, while the earthquake, for example, to raise the 3% of probability to the 70%.
Okay, thank you very much for your response. Okay, thank you.
Okay, any other questions? Yes, as far as I know, actually, Central Asia region is quite good in such kind of work, so connected to climate change and seismic tasks. So that was one of the examples. I would like to give a floor to the next presentation with the work entitled as Search for Genomic Mutations Associated with Drug-Resistant Tuberculosis. So please, you have the presenter, you have a floor now. Present yourself. Now we have, yes, we see your screen.
Oh, nice. The topic of my presentation is search for genomic mutations associated with drug-resistant tuberculosis. So today we'll talk about the purpose of this research, which data we use and how we prepare it, which single marker and multi-marker tests we used, and which results we obtained. The purpose of this research was to analyze genomic and phenotypic data and identify mutations and features related to drug resistance to the first and second line anti-tuberculosis drug. We consider it isoniazid, rifampicin, ethambutol, and streptomycin as first-line drugs, and fluoroquinolones and aminoglycosides as second-line drugs. Tuberculosis is still actual nowadays. Every year, near 10 million people fall ill with it, and about 1.5 million died from it each year. It is top 10 infectional killer. Usually it takes much time to treat it, at least 6 months, and if the first treatment failed, the recurrent case likely will be drug resistant. Drug resistance is an ability of disease-causing germs, in such cases as tuberculosis, to continue multiplying despite the presence of drugs that usually kill them. In this research, we use data collected from the drug-resistant tuberculosis project. It contains more than 1,000 tuberculosis cases with results of biological tests for drug resistance and genome sequences. At first, we removed duplicates and cases with conflicting results for drug resistance. For example, if one test system showed resistance and another insensitivity, we exclude such case. Also, we applied a minor allele frequency filter. So we took only mutations that occurs more than in 1% of samples. With help of phylogenetic trees, we identified two populational subgroups in the original data. With help of Pairwise correlation table, we found cross-resistance between first-line drugs, fluoroquinolones, and aminoglycosides, but no cross-resistance between first-line drugs and second-line drugs. Single marker tests check association between observed drug resistance and individual mutations. They are modifications of classical statistical tests. We used feature exact test and Cochrane-Mantel-Hansel test. They're both based on such contingency tables. To visualize test results, we used Manhattan plots. The higher the point along ordinate axis, the more its significance. So, for example, for isoniazid, Cochrane-Mantel-Hansel test identified two mutations with relatively low p-value. Single marker tests revealed sets of mutations associated with drug resistance to individual first-line drugs, their combinations, and groups of second-line drugs. However, they were not able to identify mutations associated with resistance to individual second-line drugs. To verify obtained results, we used the BDREAM database that includes already known mutations. The key difference of multi-marker tests from single marker is that they consider additive effects between mutations. So they consider mutation 1, 2, 3 not as individual, but their different combinations. As multi-marker tests, we used algorithm for searching for combination of mutations with boosting and factor analysis of mixed data with linear mixed model. We took genomic data and phenotypic features. With help of factor analysis, we obtained a set of uncorrelated features, and then we built a linear mixed model. This model considered fixed and random effects. Fixed effects is a base regression in the data, and random effects are effects inside each subgroup. Each subgroup may have its own unique features like specific treatment regimen in the country or healthcare system itself. So it is features that are not associated with drug resistance. To obtain model, we use cross-validation. We used 4 basic metrics: precision, recall of score, and accuracy. For the first-line drugs, scores are good. For fluoroquinolones, scores are satisfactory. And for aminoglycosides, scores are low. That means that we can build a good classifier for them. We went deep in details of this algorithm, only discuss the main idea. So we want to find different combinations of mutations and test how they're associated with resistance. So we need to enumerate them somehow, but the number of mutations is huge, and it is hard to enumerate all of them. So we want to switch from enumerating mutations to enumerating samples, because number of samples are much lower. We applied such algorithm for second-line drugs and obtained a list of mutations with informative score calculated by the formula. Despite some values are higher than another, we still can't build a classifier for them because accuracy is too low. So the correct way to interpret the results is that this list of mutations occurs more frequently in the samples that are resistant to fluoroquinolones that in those that are sensitive. So we consider a single marker and multi-marker tests that can be used to test mutations associated with resistance. This test works good with individual first-line drugs and their combinations. However, they found mutations that includes individual mutations associated with drug resistance to their second-line drugs, but they alone are not enough to build a good classifier. So that's it. Thank you for your attention.
Thank you for your very productive pressed presentation. So if we have questions, please, you may ask now. You have a chance. So we have no questions. No. Well, actually, so YouTube stream now is has a little bit in lag. So probably let's say 20 seconds. But still, so I'm not supposing that we have questions, because we have just one question, just an organizational question in the YouTube chat. If we have no questions in our Zoom, so I would like to thank you, all of you, in this session. And so now I'm announcing our break. We call it big break till 2:30. So when we will start our session called B1 about practical problems of pattern recognition and information processing. So see you 2:30. Thank you.